during a lecture entitled Discourses on Molecules, given in Bradford at St. George's Hall in 1873. James Clerk Maxwell launched into a politely veiled critique of Darwin's theory of evolution. In the heavens we discover by their light, and by their light alone, stars so distant from each other that no material thing can have passed from one to the other. And yet this light, which is to us the sole evidence of the existence of these distant worlds, tell us also that each of them is built up of molecules of the same kinds as those which we find on Earth. A molecule of hydrogen, for example, whether in Sirius or in Arcturus, executes its vibrations in precisely the same time. Each molecule, therefore, through the universe bears the impression on it, the stamp of a metric system, as distinctly as does the meter in the archives at Paris, or the double royal cubit in the temple of Karnak. No theory of evolution can be formed to account for the similarity of molecules, for evolution necessarily implies continuous change, and the molecule is incapable of growth or decay, of generation or destruction. None of the processes of nature, since the time when nature began, have produced the slightest difference in the properties of any molecule. Science is incompetent to reason upon the creation of matter itself out of nothing. We have reached the utmost limit of our thinking faculties when we have admitted that because matter cannot be eternal and self-existent, it must have been created. It is only when we contemplate not matter in itself, but the form in which it actually exists, that our minds find something on which it can lay hold. As a devout Christian, Maxwell was troubled and rejected the far-reaching implications of Darwin's theory of evolution, namely that the laws of nature could somehow organize itself into the observed structure and complexity of the universe without the apparent need for a deity. He saw the irreducible and consistent form of molecules and atoms as indicative of a creator, since to him at the time there was no understood mechanism for these forms to arise. Ironically, a few years later, scientists would actually perform what Maxwell claimed was impossible, to show how matter can arise from a theory of fields based upon the developments which he himself pioneered. Yet, I think on a more abstract level, there is some merit to his analysis. While physicists can effectively describe how fields give rise to quarks, electrons, and all the fundamental units of matter, the fact that the laws of nature give rise to such uniformity of form on the smallest level, or even the fact that these laws are comprehensible, is an interesting and profound point, which many have wondered at. In 1960, physicist Eugene Wigner penned an article entitled "The Unreasonable Effectiveness of Mathematics in Natural Sciences." In this article, he was expressing the core of a sentiment that had been bubbling up even before the birth of quantum mechanics. That is, how mathematics, developed to describe one type of physical phenomenon, can be so easily used to explain other phenomena, which had little to do with the original. Of course, from an idealistic point of view, this would seem natural, since the rise of mathematics provided a manner to represent Platonic forms in better and better ways. So, for example, while a perfect circle or other geometric shapes can be represented using a simple formula, more complex Platonic forms or ideas began to become possible to be represented using more and more complex forms of mathematics. Over the time, mathematicians have learned to express ideas as abstract as different sorts of infinities, sets, or classes of motion. In fact, one might view mathematics in general as developing a means to unambiguously represent the Platonic forms of the universe. I think it is due to this fact that some theoretical physicists, in an apparent return to Pythagorean philosophy, entertain a much more radical view of math, that it somehow represents the true nature of reality. Thus, the physical universe is not just described by mathematics, but is mathematics. This view was given particular force with the introduction of the quantum wave equation by Schrödinger and the matrix representation by Heisenberg in the mid-20s. The wave equation was introduced to describe the trajectories and behavior of subatomic particles like electrons. Without it, the behavior of electrons in the atom or diffracting through a double slit made no sense. But the new wave function presented a problem. It was explicitly non-physical, because it was, in mathematical terms, an imaginary or complex-valued object. Additionally, when evaluated to generate measurable quantities, it operated in a probabilistic manner. With Paul Dirac's incorporation of special relativity into the framework of quantum mechanics, the new field theory approach was developed to account for more than a single species of particle. However, with quantum field theory, a radical new view of the concept of a field emerged. In many physical theories, there exists a concept of a field. The idea of the field originally was imagined to have a physical basis. For example, the magnetic and electric fields were conceived to arise from a physical medium called ether. The gravitational field, when it was first described by Newton, required action at a distance. It was for this reason that Newton believed it was profoundly flawed. It was only with Einstein that the modern view of a gravitational field, described as a product of a medium of curved space-time, emerged. As we will discuss in much more detail later, with the advent of quantum mechanics, the concept of a field transcended the need for a physical medium. Mind you, a medium still exists, but it was explicitly non-physical, an abstract mathematical function that permeates all space. This new abstract understanding of the field is a large reason why Plato's idealism appears to fit well in modern physics. But this was not always so, and even today this fact seems lost in the popular understandings of the subject. I think it's safe to say that the birth of the concept of the modern field began with James Clerk Maxwell's derivation of the equations for electromagnetism. Between the years 1862 to 1864, Maxwell came up with a theoretical framework which united the electric and magnetic fields, showing that light was basically a type of wave propagating in the electromagnetic field. He demonstrated this by calculating the speed of a traveling wave in his theory, showing that it was the same speed as what had been measured for light. The field or medium which light propagated in was termed ether, because since Thomas Young's double-slit experiment around the year 1800, it had been understood that light behaved as a wave, and the different colors of light represented different wavelengths. This double-slit experiment, which demonstrated light's diffraction, later would be applied to electrons, representing a very important experiment validating quantum mechanics. There was, however, one odd thing about his theory. While it united the electric and magnetic field into one field, there was a strange thing about how relative motion was handled. Since Galileo, it was understood that fixed relative motion shouldn't affect the behavior of the laws of physics. So, for example, if I was on a train, traveling at a constant high velocity relative to the Earth, and threw a ball, the trajectories and behavior of it relative to me and everything on the train would be the same as if I was standing on the Earth, not moving. Further, if I observed this event outside the train, stationary relative to the Earth, I would see the same physics, only with the train's velocity added to all the objects on the train. This idea is encapsulated by saying that the laws of physics are invariant, or the same, for different inertial or non-accelerating frames. In Maxwell's theory, the force on a charged particle generated by a moving magnetic field was treated as arising from a different source, depending on the relative motion of the magnetic field. This is despite the fact that in both cases the strength of the force from the resultant field is the same. So, for example, if one waves a loop of wire across a magnetic bar, a force is created in the wire that can push on the electrons in the wire via the Lorentz force law, part of Maxwell's equations. However, if instead I keep the loop stationary and wave the magnetic bar to generate the exact same relative motion, the change in magnetic flux creates the force due to Faraday's law, part of Maxwell's equations. That these forces are equal is in part due to the constant speed of a wave propagating in the electromagnetic field, regardless of the relative velocity of the frame of reference. That is, the speed of light must be independent of the inertial frame. While there is some indication that Maxwell may have recognized this fact, that the speed of light was constant, it wasn't until Einstein that the constancy of the speed of light was stated and used to build up the special theory of relativity. The constancy of the speed of light explained the failure of the famous Michelson-Morley experiment to measure the effect of relative motion on the speed of light. It also suggested a startling fact, that there was no physical ether, that these electromagnetic waves were waving in a non-physical medium. With Einstein's special theory of relativity, several other important physical consequences were shown to follow. The constancy of the speed of light meant that no matter how fast or slow one was moving, the measured speed of light would be the same. Normally, when calculating the speed of an object in a moving frame of reference, one can simply add the velocity of the frame to the velocity of the object relative to the frame. For example, a ball thrown on a train with a velocity v would, if looked at from a person stationary on Earth, travel with a velocity of v plus the speed of the train. This addition of velocities didn't work for light. The profound consequences of this required that both time, length, and mass would be modified based on the velocity of the frame of reference which one inhabits. The idea that space, time, and mass could change depending on which inertial frame of reference it is observed in also demonstrated that mass was actually another form of energy. And years later, with general relativity, led to a new understanding of gravity as due to the distortion of space and time caused by mass and energy. Einstein went on to cause more problems for the standard understanding of light as waves of ether. He later explained a phenomenon known as the photoelectric effect, where when light above a certain frequency was shined on a material, it would suddenly start emitting charged particles. He explained this effect by arguing that at the smallest level, light behaves not as a wave, but as a particle, with the energy and momentum of the light parceled up into quanta of light called a photon. Later, this quantum-like absorption and emission was used successfully by Niels Bohr to model how an electron in a hydrogen atom absorbed and emitted light. Only now it was the electron's orbit about the nucleus which jumped quanta-like from higher to lower orbits. These orbits were related to its energy. But the strange thing was that these orbiting distances were discrete and well defined. In fact, the whole idea of an electron orbiting moon-like about the nucleus had a well-known and serious physical problem. Since Maxwell's equations tell us that charged particles, when accelerating, which happens when something orbits another thing, will give off electromagnetic radiation, or light. That any electron actually orbiting a nucleus in this manner would radiate all its energy away and collapse into the nucleus. This fact was well understood ever since the planetary model of the atom was proposed, yet its solution had remained a mystery. It was the French physicist Louis de Broglie who proposed a radical new idea, that electrons actually behaved like a wave. This proposal, as strange as it seemed, resolved all the problems with the Bohr atom. The electron was behaving like a spherical standing wave, with the discrete energy levels due to the different oscillating modes permitted by this system. Just like a guitar string can only vibrate at certain modes. Another bizarre thing was that when Schrödinger worked out the mathematical form which these waves must take, it turned out that they were not physical, since, as mentioned before, it was in mathematical terms an imaginary or complex-valued object. The fact that electrons can behave like waves was also shown using a similar double-slit experiment as Young had used to prove light was a wave. Only now, instead of light, a beam of electrons hit a screen containing two slits, and a second screen which registered the distribution of electrons which passed through these slits. In the case that the electrons would behave like normal particles, then two clear bands should appear on the second screen, which correspond to the two slits in the first screen. If the electrons would behave like waves, then one will see a series of high and low intensity bands appear across the whole width of the second screen. These series of bands are due to the waves interfering with each other and themselves, or diffracting. Interestingly, this is true even if just a single solitary electron were to be shot at the double slit. So in reality, the electron behaving as a wave traverses both slits at the same time. It exists in two locations at once. This ability to exist in two locations at once is also known as the quantum mechanical property of superposition. As we will learn later, superposition can exist for many other physical properties outside of just position. The debate over what this quantum mechanical wave function represented physically was somewhat resolved by 1927 with the so-called Copenhagen interpretation. At the heart of this view is Max Born's thesis that the wave function is simply a mathematical object which can yield a probability density function. Thus, it has no physical meaning outside of the statistics and its ability to predict a particle's behavior. Needless to say, physicists hated this interpretation, though it has become increasingly accepted in the ensuing 80 years. Initially, many clung to the belief that the wave function was masking some other local physics that we just couldn't measure. These were known as the hidden variable theories. To support this thesis, physicists Albert Einstein, Boris Podolsky and Nathan Rosen and others came up with a thought experiment, now known as the famous EPR paradox, to expose what was considered an absurd consequence of quantum mechanics. The fact that two particles, after interacting and becoming entangled quantum mechanically, could affect the state of each other after being separated by great distance. However, this phenomenon, which Einstein derisively called spooky action at a distance, was subsequently demonstrated through many experiments, and the notion of quantum entanglement is now not only accepted, but used to develop new technologies. In 1964, John Bell put forward his famous theorem which states, "No physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics." He further proposed an approach to test the validity of this theorem by measuring the occurrences of correlations between measured states of particles which were quantum mechanically entangled. Experiments testing Bell's inequality in 1972, 1981, and more recently 2015 have so far laid to rest any theory of local hidden variables. It was actually Heisenberg himself who grasped the connection between quantum mechanics and the Platonic viewpoint regarding the essence of reality. I think that modern physics has definitely decided in favor of Plato. In fact, the smallest units of matter are not physical objects in the ordinary sense. They are forms, ideas, which can be expressed unambiguously only in mathematical language. There are several important aspects of quantum mechanics that lend themselves to the Platonic interpretation. The first is a clear separation between the object measured and the mathematical form which gives rise to the object. To use the cave allegory, the shadow and the object casting it. Then there is, as Heisenberg acknowledged, the fact that the units of matter are not physical objects in the ordinary sense. There is also additional subtle evidence for the correctness of Plato's views, which flows from the fact that the fundamental physical interactions are governed by probability and not pure determinism. If we accept the assumption that the universe is either spatially infinite or eternal, assuming a finite difference scale, the logical consequence is that all forms are eternal, because probabilistic physics operating over any kind of infinity will most surely yield all outcomes that have a non-zero probability of occurring, even if that probability is infinitesimally small. This means in a universe with infinite space, all these forms must exist with an infinite number of occurrences. And even if the universe is eternal, all these forms would occur an infinite number of times. In fact, the only escape from an infinite multiplicity of identities is offered by the idea of a unique human soul. Either way, death and decay would seem to be an illusion, a simple product of our limited sampling. It's safe to say that we are currently in the midst of a mini renaissance in our understanding of questions related to the fundamental nature of quantum mechanics. I believe this has in part been fueled by the recent drive to develop quantum computing, which at some level has forced applied and theoretical physicists to try and resolve these outstanding issues. Additionally, in recent years, there have been some profoundly interesting and exciting theoretical developments in string theory and the decades-long quest to understand how gravity might arise within the framework of quantum field theory. These ideas suggest that the very construction of space-time is a product of quantum entanglement or quantum correlations. Here, the quantum entanglement structure, which builds up space-time, retains quantum information about the whole system on the boundaries. Thus, the very construction of space-time in this model represents a type of error-correcting code. The upshot of all these new understandings is that fundamentally, relational information may not only underlie matter, but also the very structure of space and time which we inhabit.